Hello and welcome to my presentation. My name is Andre Truxa, and I will be assessing the reliability of LiDAR SLAM data in Costa Rica's tropical dry forest through DBH. So first we must ask ourselves, what is SLAM? And it stands for Simultaneous Localization and Mapping, and it's an emerging LiDAR technology in forestry modeling. It's typically worn on a backpack held by an operator, allowing the scanner to move through the forest. So the pros of SLAM is that it takes less time to complete scans of entire plots than traditional methods or TLS, which is a static laser scanning. And it also could reduce existing errors and faults in the collection of tree metrics through LiDAR. So that includes occlusion and shadow effects, which is basically obstacles blocking the scanner. To assess the reliability of LiDAR SLAM, we must compare it to a true method. So this is a tried and true method using DBH tape and going to every tree in the plot. And this is in comparison to the test method, which is with the LiDAR Velodyne 32E, a multi-beam laser scanner shooting 32 beams of light and acquiring 1.4 million points per second. In order to localize itself, it has an integrated IMU Novatel STIM 300. And here we can see it being set up, how it looks in the box, and specifically the head of the laser scanner, which rotates to collect points. So this brings me to my main objective, which is extrapolating tree metrics. I want to extract a variety of metrics that includes canopy height, tree height, crown area, shape and volume, DBH, and liana volume. You will see that DBH here is highlighted because I will be specifically focusing on this metric for this project. I will be also asking whether or not the reliability of LiDAR SLAM changes with successional stages or different tree sizes. And here we have descriptive statistics of the difference between the traditional, which is the tape, and the LiDAR SLAM method. Here you can see that we are really close to zero difference in the median and the mean, but you will also notice that we have pretty large outliers for the minimum and maximum values. Here is the overall distribution of the data. As you can see, there are some outliers on the left and right side of the histogram and on the box plot, but you will also see a heavy concentration of the frequency near zero, and this is an indicator of LiDAR SLAM data being accurate. Now, if you look at the descriptive statistics of the difference between the traditional and LiDAR SLAM method by succession stage, we will see once again that the median and mean are all very close to zero. However, intermediate successional stage have greater outliers than the other two successional stages. And here once again are the histograms and box plots of each successional stage. You will see, as previously mentioned, the outliers are greater in the intermediate successional stage. But once again, each successional stage has shown a huge concentration at the number zero, which is once again a sign of LiDAR SLAM data being accurate. Here are the descriptive statistics split by tree size. The size is classified by each tree's true measurement with the DBH tape. And here you will see a greater variance in trees with a DBH greater than 40 centimeters. So the minimum, as you can see, is minus 56, whereas the maximum is just under 2. So we can see that the LiDAR SLAM tends to underestimate the thicker trees. And here we have a distribution based on tree sizes. We see that there are only a few strong outliers skewing the 40 plus centimeter category, And we can also see, based on the scale of the histogram, that the 10 to 19.9 centimeter category tends to be estimated very accurately. And this takes me to my conclusion that despite a few outliers, LiDAR SLAM is a generally reliable method to accurately measure dBH, regardless of successional stage and tree size. Thank you for listening.